another quick fact for fun. A transpose A and A transpose are guesses? Fill in the blank?
Not equal.
Oh, good. Yeah, generally not equal. That's good. One, are they both defined?
Not necessarily.
Wait.
It could be, but it's not a guarantee, I think.
Could be defined, but not necessarily?
I think they would be defined, because you would have, for A transpose A, you would have, going with that n by n example.
Okay, so let's suppose A is m by n. This is just us like thinking, right?
Yes, so for the A transpose A option, it'd be A n by m.
Okay, hang on. So A transpose then is n by m?
Times A, which would still be n by n.
Okay, so A transpose is n by m, and I'm multiplying by A, which is m by n. And so this whole thing
Is an n by
is
n.
n by n.
And it would be the same general idea for A transpose, except it would be n by n matrix.
Good. So they're both defined. They have to be defined, which is weird. You see that? So they're both defined, but they're both, oh, well, and they're both square, right? We talked about that last time. So they're both defined, they're both square, but they're not necessarily the same size. You guys see that? So the fact that they're not necessarily the same size would give me this, and they're generally not equal to one another. You could ask a very reasonable question, which would be, in the case that they are the same size, would they be equal to each other? The answer is generally no, but that would be an interesting question. I believe it's actually a no. Find a pair of matrices that aren't. Or find a matrix so that these two matrices aren't the same thing. It's not super duper hard. I wanted the blank in here to be filled with a different word. Starts with an S.
Symmetrical.
Symmetric? I don't know how to spell. Do you ever take spelling? Okay, so how would you go about showing this? Like, for one thing, symmetric matrices are always square, right? Why? What does symmetric mean? You guys remember?
Transpose itself is the same thing.
Good. So symmetric means, i.e., A transpose A's transpose should give me A transpose A. You guys see that? Dude, what the hell?
I don't know if this is a good way to think about it, but I would think of it as A transpose equals A if they are symmetric.
Yeah, so these guys are these two matrices, A transpose A and A transpose, are automatically symmetric regardless of the matrix A.
Okay.
You guys see that? That's why this is weird. Does that make sense? first let's just check this. You guys with me? So, by way of proof, right, we're going to consider A transpose A's transpose. And the way you transpose a product, right, that thing we just did a couple minutes ago. Actually, let me... I want to color code this a little bit so that you can see what the hell I'm doing. So I'm going to color code this first matrix A transpose in blue. That's just so you can see where it's moving, right? So we just talked about when you're transposing a product, you reverse the order and transpose both things, right? So my first matrix is going to be A. So we're going to say that this is A transposed. And then you put in your A transpose, and you have to transpose this thing. You guys with me on that? This is really me thinking AB transposed is B transposed, A transposed. Everybody with me on that? Okay. Now, I get that the first piece is A transpose, and the second piece is A transpose, transpose. So you flip it over its diagonal and then flip it again, right? Swap the columns into rows and then swap the rows into columns. Gives you back the thing you started with. With me on that? Okay, and the fact that this matrix transpose was that matrix means that this thing is symmetric. Right, a symmetric matrix is one where S transpose is S. Is all on board? How do you do the other one?
Thank you.
So I just did this one is symmetric. You guys see that? How do you do the other one?
Transpose the other one
Yeah, take this thing and transpose it, right? So we're going to consider instead, so I guess the proof of, like, part A, I guess, proof of part B. We're going to consider our matrix A transpose. Oops, I need a color code. I'll put the blue thing first again. This thing's whole transpose. And that's going to be, oops, that's going to be the black one, A transpose transposed, and then the blue one, transposed. And we'll get to A transpose. Check these. Make one of these with full dudes.
Yeah, for QED.
I don't like that. Okay. Questions? This seems really stupid, right? This is like the funniest, dumbest thing. You're like, yeah, Joe, duh. Like, did you make up this little fucking thing just to use the word symmetric? And the answer is, no, I did not. This is really cool. This has an application later. Save this in your head. When we do linear regression, we'll need it. It's really weird. It's one of the things I absolutely love about this subject. We get about halfway through this book, and then we're like, oh yeah, BT dubs, we can do linear regression now. In fact, we can do polynomial regression, it's all the same shit. And this matrix makes a crucial appearance there. And you need it. Like, it's the weirdest damn thing.